Real-world business data is chaotic and unstructured, but that information eventually hits the rigid architecture of enterprise back-end systems, operating entirely on relational logic. This creates an immediate architectural tension. Large language models are probabilistic text generators. They guess the next likely token. Enterprise pipelines demand absolute deterministic outputs. A probabilistic model attempting to fill a rigid database slot inevitably generates cascading syntax errors that break downstream applications silently. Relying solely on natural language instructions to guarantee data structure is a critical anti-pattern. You cannot fix a structural mismatch by infinitely tweaking your prompts. Successful production architecture requires building programmatic, deterministic wrappers around the model's probabilistic reasoning. When developers encounter high false positive rates during extraction, the initial reflex is to append ad hoc qualitative instructions to the prompt, like be conservative or only report high confidence findings. Language models do not evaluate their own confidence mathematically. Applying confidence-based filtering shifts the evaluation threshold at random across different datasets, failing to improve precision. High false positive rates rapidly undermine developer trust. If a system continuously surfaces inaccurate findings alongside accurate ones, users lose confidence in the correct data and begin ignoring the system entirely. The programmatic alternative removes heuristics entirely. You replace qualitative requests with explicit categorical criteria baked directly into the system logic. Resolving systemic ambiguity is a structural engineering problem, not a vocabulary problem. This side-by-side comparison shows the difference in baseline logic. Instead of a vague request to flag serious errors, the structured prompt establishes explicit, categorical criteria defining a severity 1 bug. Those definitions are then paired with concrete code examples to achieve consistent classification. Text instructions alone will still fail on structural edge cases. When a model encounters a varied or unpredictable document layout, it often fabricates data to satisfy the prompt. Few-shot grounding is the primary architectural defense against unpredictable source structures. By embedding 2 to 4 targeted examples in the prompt, the model stops attempting strict pattern matching and begins generalizing its judgment to novel, unseen situations. These few-shot examples must explicitly demonstrate the reasoning process. They need to show exactly why a specific action or tool was chosen when the source context was ambiguous. Explicit criteria and few-shot examples set the baseline for intellectual precision, but they lack the physical enforcement mechanism required for deterministic enterprise architecture. To build that physical enforcement, we transition from prompt engineering to the Claude API, specifically utilizing the tool use parameter. Requesting JSON output inside standard markdown blocks is a fragile legacy approach. A single hallucinated bracket or missing comma will break a production pipeline. Binding the tool use parameter to a JSON schema mathematically eliminates syntax errors. Setting tool choice to any guarantees structure while forcing a named tool executes rigid pipelines. However, forcing required fields risks data fabrication when source documents are missing information. Configuring specific fields as optional or nullable maintains data integrity. It gives the system permission to return empty values when encountering incomplete source texts. For extensible, ambiguous categorizations, you configure enum fields paired with other or unclear string patterns to handle edge cases safely. Tool use and JSON schemas act as the physical enforcement layer, guaranteeing syntax and structure for downstream databases. This pipeline validation node demonstrates the limitation of structural enforcement. It guarantees syntax, but cannot prevent semantic errors, like extracted line items failing to sum to the total. We handle this by building a retry-with-error-feedback loop, acting as the mandatory safety net. When semantic validation fails, the script captures the specific error and appends it to the original prompt. This triggers the model to evaluate its own mistake and self-correct. Retry loops have strict limits. They successfully fix formatting or logic, but they cannot conjure information that is physically absent from the source context. To monitor system health and edge case failures over time, we implement extraction telemetry. Embedding a detected pattern field within the schema enables systematic analysis of exactly why developers are dismissing specific findings. Production architectures must assume failure. Semantic validation loops are the required mechanism to upgrade basic structural compliance into true data integrity. Single document validation is easily manageable. Operating at high volume, concurrent production scale introduces heavy cost and latency trade-offs. Synchronous APIs are necessary for blocking workflows like pre-merge CI checks where the system must wait for an immediate response. For non-blocking, latency-tolerant workloads like nightly document extraction, the Message Batches API is the necessary architectural choice. The business trade-off is clear. Utilizing batch processing yields up to a 50% cost savings in exchange for a processing window of up to 24 hours. The Batch API has a strict architectural constraint. It processes discrete requests and does not support multi-turn tool calling within a single request. This diagram shows the requirement of implementing custom ID fields to accurately correlate asynchronous batch responses with their originating requests. System scale dictates API selection. Optimizing cost requires separating synchronous logic from asynchronous batch execution. This flowchart maps the pipeline's 4 phases. Stage 1. Explicit criteria and few-shot examples form the baseline. Stage 2. Tool use and JSON schemas enforce syntax compliance. Stage 3. Semantic retry loops guarantee logical consistency. Stage 4. The Batch API optimizes for enterprise scale. Enterprise-grade AI integration requires abandoning the fragility of prompt tweaking. Reliable extraction pipelines rely on designing resilient, programmatic wrappers around probabilistic systems.